Today we're going to learn two new hand rules, but before we do that, we're going to review the one that we learned yesterday, which we called the wire grasp rule. If you remember, the wire grasp rule was simply used to find the direction of the magnetic field that was caused by an electric current or moving charges. For instance, if we have a moving charge going in the direction indicated by this X, which means, by the way, what? It means away from us. It means into the page. If we have an electron, let's say a negative particle going into the page, we know that the magnetic field that surrounds that is going to be circular. In fact, a series of concentric circles getting further and further apart from each other, indicating that the field gets weaker and weaker as you get further away from the moving charge. But what about the direction? Well, this wire grasp rule says what? Well, it's a negative particle, so we use your left hand, right? If it was a positive particle, we just use our right hand. This is negative, use your left hand. Okay, put your fingers and your thumb perpendicular to each other and don't change that. You can bend your fingers all you want, but they still stay perpendicular to your thumb here. Which way does my thumb go?
The direction of the current.
The direction of the current or the moving charge, which in this case is into the page, right? So stick your thumb into the page, right? And then what are you going to do with your fingers? Curl them up, bend them up, right? Doesn't matter how much you bend them, just a little bit or a lot. Okay, it doesn't matter where you put them. Okay, it's not really hard that way. You don't have to get confused about that. Just stick your thumb into the page in this case, bend your fingers a little bit, a lot. It doesn't matter. In the end, we would find in this case that the magnetic field goes, in this case, counterclockwise. Okay, if we do a wire or even just a moving charge, it doesn't really matter, going this way, again, a negative particle, what's the magnetic field look like? Well, it's circular like this around it, either this way or this way. How do we figure out which way it is? Thumb in the direction of the particle. Where are my fingers right now? Above it. Which way are they pointing? Okay, so the magnetic field in this case would be into the page above the wire. Okay, right now, where are my fingers? Below it, they would be pointing out of the page, represented by a dot, right? Right now, where are they? In front of the wire, and they're pointing up. And right now, twist my body around here, right now, where are they? Behind the wire, and which way are they pointing? Down the page. Does that make sense? Yep. Yeah, I split that arrow just to indicate that it's behind the wire. Okay, if you don't like that symbol, it's not really a big deal. Just express it in words. Okay, what they probably do on an exam is draw a better three-dimensional picture. I just don't want to try to go there because I'll just mess it up and confuse you if I try to do that. Okay, as long as that symbol makes sense to you, good. Okay, if you don't want to use it, that's okay. It's not really a big deal. Okay, this is like these two symbols, you'll see that a lot. That's very commonly used and it's universal. Okay? The other two symbols is as much mine as my way of doing it as a general way. All right? What if I said, here's a good one. What if I said I had a wire like this, and I had an electric current, an electron current versus conventional current. Remember what conventional current means? Yeah, the flow of positive charge. We have that on our little board over here of things to remember, right? Conventional current equals positive charge, in which case we'd use our right hand. This is electron current, though. Okay, we're going to use our left hand. But the question is not which way does the magnetic field point. The question is, one simple question. On the left-hand side at point P. Now that point P is a dot. That doesn't mean it's out of the page. Okay, it's just representing a place. Does that make sense? At point P, which way would a compass point? Which way would a compass needle point at point P? What am I really asking you? Yes? Yes? You could not be more correct on that. What am I really asking you when I say which way does the compass point at point P? Yeah, I'm asking for the direction of the magnetic field. How do you find the direction of the magnetic field at point P? Use the wire grasp rule, right? That's all I'm doing. It's the same question as I just asked you over here, except that the wire is pointing downward as opposed to pointing to the side, to the right. So we would say in this case, once again, my thumb points downward. My fingers, I want my fingers to be to the left of the wire. This is where they are right now, right? Which way are they pointing? Out of the page. So the magnetic field would be, I have that represented by a dot, but that's coincidence. Okay, point P, the magnetic field would be out of the page, and a compass needle would point out of the page, because compass needles point in the direction of the magnetic field. Right? You guys okay with that? That's the first of the 3 hand rules. Okay, you will see this, I promise you right now, okay, you will see wire grasp rule on your unit test and on your unit assignment. Guaranteed. Okay, and almost certainly on your diploma exam. I can't promise anything about your diploma exam because you'll see it before I do, but it'll almost certainly be on your diploma exam as well. All right. I want to give you the second rule now, the second hand rule now that we're going to call the Coil Rule, or at least that I call the Coil Rule. For solenoids, whatever. Just call it the Coil Rule if you want. A solenoid, by the way, is just a coil of wire. So if I take a string of wire and kind of wrap it around like this and apply an electric current through it, that would be a solenoid. Would generate an electromagnet, right? Maybe you've done that in elementary school when you were doing magnetism. You take a nail, you wrap a wire around it, you hook it up to a battery, and then you pick up thumbtacks with it, or you pick up paper clips with it. You made an electromagnet. That's a solenoid, a coil of wire. There's a rule that we call the Coil Rule that allows us to find the magnetic field caused by that solenoid to essentially what it boils down to is finding the polarity of that electromagnet that you've just generated. And it's a rule that is similar to, but yet very different from, and I'll explain that oxymoron in a second. It's similar to, but very different from, the wire grasp rule. It's similar to the wire grasp rule in that you will use your thumb and your fingers at 90 degrees to each other. You will bend your fingers. So it's going to look very much like the wire grasp rule, except that this time your fingers, your bent fingers, will point in the direction of the current or the moving charges, and your thumb will point in the direction of the magnetic field. So it's opposite. It's the same variables there. It looks the same. Your hand's going to look the same. If I was to look out at you doing a hand rule, and it was the wire grasp rule or the coil rule, I wouldn't know which one you were doing without looking at the question. But you would know that your thumb and your fingers get reversed for this one versus the wire grasp rule. And by the way, when I say your thumb points in the direction of the magnetic field, you've got to be careful with this. It's the magnetic field inside the solenoid or inside the coil of wire. And that becomes really important in a couple minutes when we do an example. Now, there's a picture of it up here, but in the end, I'm going to demonstrate it for you. We're going to do some examples of it, so I wouldn't necessarily try to draw that diagram. If it was me trying to draw the diagram, we'd end up further behind. We'd end up knowing less after the diagram than before the diagram. Let's do an example of this. When I draw this, I'm going to draw it with like a steel bar or an iron bar in the middle. Understand that we don't have to have a steel bar or an iron bar or something ferromagnetic inside this solenoid or inside this coil. We draw it that way for a couple of purposes, for a couple of reasons. One because it will be a stronger effect. Your electromagnet will be stronger if you have a piece of steel inside this coil than if you don't have a piece, because it kind of stores the magnetism. Does that make sense? You still get it. You get the effect without the ferromagnetic material inside, but you won't store anything. It'll just be the magnetic field that's generated at any given point in time by the solenoid. The other reason that we draw it in there is because, honestly, it's easier to see the drawing. It's easier to understand what I'm trying to show you in the diagram if we have that in there just as a little bit of a spacer. So understand that it doesn't have to be there, okay? But if it is, it magnifies the effect and it makes the diagram easier to see, easier to understand. This is my coil. Do you see what I'm doing there? The wire wraps around, right? Kind of then in behind and then wraps around like this. If this is my coil, let's wrap up this piece of paper. If this is my coil, the wire is going up like this. Okay, can you see? There you go. You guys are laughing at my artistic ability just a minute ago. And this isn't all that bad, right? Say we got a battery set up like this. By the way, we've talked about this briefly before, but if you forget, the short end of the battery is always the negative terminal, and the long end of the battery is always the positive terminal. Sometimes on an exam they label that for us, positive and negative. Sometimes they don't. So you need to remember that the short end is the negative and the long end is the positive. This means that the electric current will go this way. The electric current is going to leave the negative end, that is the electron current. If we thought of it as conventional current, it would go the other way. It really wouldn't matter. It would give us the same answer. Okay, if we use the electron current, we use our left hand. We use conventional current, we use our right hand. But we end up getting the same magnetic field either way. So we have our electrons going clockwise here, up in the front, down in the back, up in the front, down in the back, up in the front, down in the back, and then around back to the positive terminal of the battery. What does the magnetic field generated by this solenoid look like, or this coil look like? What is the polarity of this coil? This is an electromagnet now, right? We can pick up our thumbtacks at a junkyard, at a car junkyard. Like that's what they use to pick up cars, is these massive electromagnets that are hooked up to these massive power supplies. What's the polarity of it look like? Which end is north and which end is south? Here's what I want you to do to help you to figure this out, beyond the coil rule for solenoids that I just taught you a second ago. I want you to take a piece of paper, piece of scrap paper. So when you have your scrap paper, you're going to take your piece of scrap paper, you're going to roll it up and make a little coil, make a solenoid. And after you've got it coiled up here, rolled up like this, you're going to take a little piece of masking tape, and you're going to tape it so it stays that way. Now, what I'm about to do with you is going to seem silly. It's going to seem like, well, I don't need to do that because, like, I'm smart enough that I don't need to write this on there, but do it anyways. Okay, trust me, do it anyways. I want you to take one side of your coil that you've just produced, take a pen, pencil, whatever, and I want you to write the word front on it. Just like this. And on the other side, I want you to write the word back. Got it? When we do this coil rule for solenoids, and we use this little solenoid that we've just made as a manipulative to help us out here, you're going to always look at the word front. You're going to always look at the word front. Now, when I'm demonstrating it to you with my little solenoid that I've just made, I'm going to look at the word back. But that's because I want you to be looking at my word front. Okay, does that make sense? So here's what we do now. Using the coil rule, which says not thumb current fingers field, but rather fingers current thumb field, what I want you to do is to take your fingertips, your left hand fingertips, put them on the word front, make sure they're pointing up, because in this diagram, you can see the current points up in the front. So make sure your fingertips, okay, make sure your fingertips are on the word front pointing up, like this. Then I want you to curl them around and see which way your thumb points. Which way is your thumb pointing? Remember, you're looking at the word front. Okay, don't twist this around so that you're looking at something else. Okay, look at the word front. And make sure your left hand fingertips are pointing up on the word front. Wrap your hand around. Your thumb will automatically point to the right. If it's easier, by the way, we know that the current is up in the front. Which way is it in the back? Down in the back. So if it's easier for you just physically to move your body this way, you can put your fingers down in the back. Either on the word front pointing up or on the word back pointing down. Either way, your thumb will point to the right. Can you see that? Okay, if your thumb points to the right, then that means the magnetic field inside the coil points to the right. That means the polarity of this coil is what? Which end? What is this end? North or south? It's south. The magnetic field inside a magnet goes from south to north. This is really the only time this unit that we see this, that we have to worry about the magnetic field inside. We almost always think about it as going from north to south, right? Because we're almost always looking at outside. But here we're looking at inside. It goes from south to north. Now, we could extend that field line to go around like this. And you can see that outside of this solenoid, the magnetic field goes from north to south. Okay, let's do another one. Say this time we've got our core like this. Although remember, we don't actually have to have that core there, right? We've got a wire that goes around like this. We've got a battery that looks like this. Which end of the battery is positive, which end is negative? Top side, positive or negative? Positive. Bottom side is? Negative. Good. Which way does the current go? Clockwise or counterclockwise? Which way is the electric current going to go as a result of that? Does the current leave the negative or leave the positive? If we're talking about electron current, it leaves the negative, so it's going to go around like this. It's going to go to the right and front, to the left and back. It's going to go around counterclockwise, right? Nothing magnetic yet. Now it's time to do the little magnetism thing. Take the coil that you just made, point it vertical this time, look at the word front. Look at the word front. Stick your fingertips, right, your fingernails, on the word front, pointing to the right. Or it could be on the word back, pointing left. Either way. I got them on the word front pointing to the right. Curl my fingers around a little bit. My thumb points which way? Down. So the magnetic field here inside the coil will be down, which means that this is going to be a north end and this is going to be a south, because inside a magnet, the magnetic field goes from south to north. Try another one. There's my core, which I don't really need, as you know. There's a missing space for a battery. There's a battery there, but I have just haven't drawn it yet. I'm going to give you the polarity of it. This is north, this is south. I want you this time to tell me the polarity of the battery. Okay, is this side positive and this side negative, or is it the other way around, negative and positive? Once again, we're going to do the coil rule, but we're going to kind of do it backwards. Instead of saying fingers in the direction of the current thumb field, we're going to say we know my thumb points in the direction of the field, and we know the field inside the coil goes from south to north, which is to the left. So looking at the word front on the coil that you guys made with your piece of paper, I'm going to stick my thumb on the word, in the front. I'm going to stick my thumb to the left. Okay, stick my thumb to the left. Curl my fingers around. Put them on the word front or on the word back. It doesn't really matter. If I put them on the word front, which way are my fingers pointing?
Left. Oh, down.
My thumb is pointing to the left because we know it goes from south to north. My fingers are pointing down. If it's too hard to do that, put them on the word back. Which way are they pointing on the word back? Up in the back or down in the front? All right, if the current goes up in the back or down in the front, then it means the current's going around this way, which means this side of the battery is going to be what? Positive, and this side is going to be negative. So the battery is going to look like this. Does that make sense? Okay, I'm going to give you one now for you to do yourself, and then in just a couple minutes, once you've had a chance to work through that, then we'll take a look at that just to make sure that you're doing it right. So this time, once again, we've got a horizontal here. This time we've got it set up like this. Okay, this time I'm going to give you the current is down in the front. I want you to label two things. One, the polarity of the magnet that's just been generated by this electric current, and the battery. Tell me which end is positive, which end is negative of the battery. Okay, give you a couple minutes to work through that. Ask me a question if you're having trouble with it, but then we'll go over it in a couple minutes anyways. Okay, let's have a look. Who's got the polarity of it now? Who votes, who says this side is north? Okay, who says this side is south? Okay, let's take a look at it here. We know that the current goes down in the front. We're told that. That's given to us. Okay, so we're going to look at our little manipulative that we've made. We're going to look at the word front, and we're going to make sure that our fingertips are pointing down in the front, on the word front. Or, if that's too hard for you to do, manipulate your body that way, then make sure your fingers are pointing on the word back, pointing up. Make sense? You're always looking at the word front. Make sure your fingers are either up in the back or down in the front. Doesn't really matter. Okay, when we do that, which way does my thumb point? Points to the left. So that means the magnetic field inside the coil is to the left, which means that this end of the coil is what? North or south? This is going to be north, and this one is going to be south. Now, I could extend the magnetic field lines around like this outside if I wanted to. That wasn't the question. Still don't have to, but I could if I wanted to. What about the polarity of my battery here? If the electric current is going down in the front, okay, down in the front, up in the back, it's going to come around like this, which means that this side of the battery right here is going to be the long end or the short end. Positive, so it's going to be the long end, and this is going to be the short end. Okay, we got that? Yes? Okay, let me give you one more. One more, and then we'll move on here. Sorry, I messed that up. Let me redraw that. Okay, almost the same question. virtually the identical question. I've got my electric current going down in the front, which would mean the same thing as saying up in the back, right? Up in the back, down in the front. Okay, I want you to tell me the polarity of the magnet, and I want you to tell me the polarity of the battery, which end is positive, which end is negative. Okay, give you a minute to work on that one, and then we'll take a look at that as a group. All right, some of you may have predicted what the answer was going to be for this one just by looking at it, right? It looks like everything's going to be opposite, because the wire, you can see here in the first diagram that we have up on the board, kind of starts in the front and goes in the back. This one starts in the back, it kind of goes in the front, so you think it's going to be opposite, right? And sure enough, it is. Let's just double check that, though. We take a look at our little manipulative that we made a few minutes ago, our coil here, our rolled up piece of paper. Look at the word front. This time my current is going down in the front or up in the back. Doesn't really matter where you put your fingers, either in the front or the back, but make sure they're pointing in the right direction. Down in the front or up in the back. Either way you look at it, part of this is going to be backwards. Part of it is not going to be backwards, right? Either way you look at it, the thumb still points toward the left, which means the magnetic field here is going to be the same as it was for the last one, which makes sense, right? Okay, on second thought, it makes sense that the magnetic field will look the same when you have a current going down in the front, up in the back. But what causes that is going to be a battery that is opposite, because that means that in order for the current to go up in the front, down in the back, we have to have our current going around like this, which means that this will be the positive side and this will be the negative side of the battery. How many people got that? Good, good. You guys feel comfortable with that? Okay, let me give you a couple little applications of wire grasp rule, coil rule, and so on. Not so much applications where we have to actually use those rules, but applications of technologies that are produced knowing that these magnetic fields are as they are. You guys have these photocopied for you, these two examples photocopied for you in the example question booklet that I gave you at the beginning of this unit. What is this? It's a speaker, right? Okay, it's a speaker that you hook up to that's in your car, it's hooked up to the stereo in your car, or it's a speaker that's in your earbud, or it's a speaker that is maybe connected by a wire or by Bluetooth to your phone so that you can listen to music in your room or your living room or something. You can see that the speaker consists of wires that have an electrical signal. It's hard to see this on the board here, but there's an electrical signal that goes through this wire. Where does that electrical signal come from? Well, if you speak into a microphone, it generates an electrical signal. Okay, if you press play on your iPhone, it generates an electrical signal that goes to the speaker. That's where it comes from. Okay, it's the music, it's the digital signal being converted to electricity. And that electrical signal goes through wire and around a coil. What's another word for a coil here? A solenoid, right? When that generates a magnetic field. Agree? So now we've got a magnetic field that's generated by this solenoid that comes from the electric current, that comes from ultimately the sound that was either the recording on your phone or the sound that's coming from your voice going through the microphone. That magnetic field we'll call magnetic field number 1, okay? B1, that's caused by this coil. But notice there's a permanent magnet here. A magnet that was already there. We're going to call that B2, magnetic field number 2. Now you get two magnetic fields. Okay, what is that going to do? It's going to cause attraction or repulsion, right? Now notice this permanent magnet is attached to this cone. This cone is usually made out of some kind of paper or felt type material. And as this permanent magnet gets attracted to or repelled by this solenoid, depending upon the polarity of the solenoid, north or south, right? Then it pulls the cone along with it. So as this permanent magnet moves back and forth, depending upon the polarity of the solenoid, the cone moves back and forth with it. Now, how does that generate sound? Well, a cone moving back and forth will generate either, it's coming towards you, it generates a high pressure in the air. If it comes back, it generates a lower pressure. And that's sound, right? Areas of high pressure and low pressure in the air. That's how the sound is generated, by this cone pushing against the air or pulling back from the air, generating a high pressure or a low pressure. So the electricity goes through the solenoid, generates north and a south pole, which causes the permanent magnet that's attached to the cone to vibrate back and forth, attracted or repelled. And that's what causes the high pressure and low pressure in the air and causes the sound. Any sense? As the electrical signal changes, then the polarity of the solenoid changes. And as the polarity of the solenoid changes, the attractiveness or repulsiveness of the permanent magnet changes. And what do we end up getting? A different sound. Right? A different sound because of the different movement of the cone. Good? Do you have to know the details of a speaker for your exam? No. Okay, well, what we want is for you to be able to work through something like this, probably something like this that you've never seen before. Okay, take a look at this one. What is this? It's also on the photocopy that I gave you. What's this?
A bell.
It's a bell. It could be a fire alarm bell, right? It could be a doorbell. When I was a kid, one of my friends had a doorbell. It was like this. Okay, doorbells that we have, most doorbells that you see are the ding-dong doorbells, right? Which are still partly based on this technology. This is like a doorbell that would just ring ding, 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 as long as you're holding onto the button. Okay? One of my friends when I was a kid had that. If you just pressed it, it would go ding, ding, and it would stop. You had to hold the doorbell in order to keep making the sound. And it sounded like a fire alarm, right? A fire alarm in a school or a mall or whatever. That's what this is. How does this work? Well, we've got a battery here, negative side of the battery, positive side of the battery. The electric current's going to go this way, right? That electric current goes through this little rod right here that has what we call a make-or-break contact. That make-or-break contact is touching, as you can see right now, is touching this thin little piece of metal right here, which carries electricity back through here, around the solenoids, around the other solenoid, and then back around, as long as the switch is closed, back around to where it came from. Make sense? Now, as the electrons flow here through this, as the electricity flows through this, these solenoids become magnetized, right? They develop a polarity. We could determine the north pole, the south pole by that coil rule that we just learned about. It develops a polarity. And they become electromagnets. As they become electromagnets, they attract this thing. They attract this thing that's connected to this hammer. So what happens? As this blue piece of steel gets attracted to the electromagnets, the hammer comes over and hits the bell. So what do we hear? Ding. That's it. We hear one ding. But what happens in that, like, that's not a very good fire alarm, right? Or a very good doorbell. Ding. So what happens in that process? Well, as this piece of blue steel comes over and causes the hammer to hit the bell, as it comes over here because of that attraction, then this comes with it. This piece of wire comes with it. What happens now? What just happened at this make-break contact? Contact was made, now it's broken. So what happens to the electric current? It stops. And as the electric current stops, this spring pulls it all back. What happens? The contact is going to be made, and then electrons start flowing, and what happens? Gets attracted, and it goes ding. Contact is broken, spring pulls it back, contact is made, ding. Contact is broken, and so on and so on and so on. And that happens like 60 times per second. So you get ding, 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 ding. Okay, and that's your fire alarm or the doorbell of my friend when I was a kid. Okay, does it make sense? These are pretty simple examples of technology based on this, right? We said yesterday that this is probably the most important technological discovery ever. These are pretty simplistic examples of it, but you can see where at least we start applying this stuff.